Look up at the night sky on a clear evening, and it's easy to feel a sense of peace and order. The stars seem fixed, the galaxies serene, as if the universe moves with clockwork precision. But what if I told you that some of those breathtaking galaxies are spinning in entirely the wrong direction, defying not only our expectations, but the very laws we thought governed the cosmos? This isn't science fiction. It's one of the most compelling and unresolved mysteries in modern astronomy. Galaxies, those immense islands of stars, gas, and dark matter, are supposed to follow certain rules as they rotate, shaped by gravity and momentum over billions of years. Yet when astronomers train their most powerful telescopes on the depths of space, they keep finding stunning exceptions: spirals whirling backward, disks spinning against the flow, entire systems that simply shouldn't behave the way they do. This isn't just a curious footnote in an astronomy textbook. The mystery of why galaxies spin the wrong way strikes at the heart of our understanding of the universe. It hints at forces we haven't yet detected, physics we haven't yet written, and histories we haven't yet uncovered. Even with instruments like the Hubble and the James Webb Space Telescopes pushing the boundaries of observation, this puzzle remains frustratingly out of reach, a cosmic secret that keeps its cards close. What could be causing Chinese letter rotations? Is it dark matter behaving in ways we never predicted? Could colossal collisions between galaxies leave behind traces of chaos? Or are we witnessing the influence of something even more profound, something that challenges the foundation of cosmic mechanics as we know it? In this video, we're going to embark on a journey to the very edge of understanding, a deep dive into the science, the speculation, and the stories behind one of astronomy's greatest enigmas. We'll explore groundbreaking research, controversial theories, and the tantalizing clues that have left even the most brilliant minds in astrophysics searching for answers. You'll see why this mystery matters not just to scientists, but to anyone who's ever looked up at the stars and wondered how it all works. So settle in and open your mind to the possibilities, because by the end of this exploration, you may never see the night sky or our place in the universe quite the same way again. Think of a galaxy not as a static painting of stars, but as a grand, slow-motion whirlpool in the cosmic ocean. Each of these immense structures is a gravitationally bound system, where everything from individual stars to vast clouds of gas is in a constant, graceful dance around a common center. This rotation is a fundamental characteristic, a memory etched into the galaxy from the moment it began to form. Billions of years ago, as a primordial cloud of dark matter and gas started to collapse under its own weight, even the tiniest bit of initial motion, a slight tug from a neighboring density fluctuation, would have been amplified. This is the principle of the conservation of angular momentum, the same physics that makes an ice skater spin faster when they pull their arms in. As the cloud shrank, its spin accelerated, flattening into a disc shape with a central bulge, much like a spinning ball of pizza dough stretches out into a wide, thin crust. This process naturally imparts a specific direction of rotation, a spin axis that should, according to our models, be a predictable and stable feature throughout the galaxy's life. Within this rotating disk, the motion isn't uniform like a rigid record on a turntable. Instead, it follows what's known as differential rotation. Stars and gas clouds closer to the galactic center complete their orbits much faster than those out in the distant spiral arms, all governed by the invisible gravitational grip of the galaxy's total mass. For a long time, astronomers expected that this gravitational force, primarily from the visible stars and gas we can see, would weaken with distance. They predicted that stars on the outer edges should therefore orbit more slowly. However, observations revealed something startlingly different. Stars in the outer regions orbit at nearly the same high speed as those closer in. This was the first major clue that our understanding was incomplete, leading to the groundbreaking proposal of dark matter, an invisible form of matter whose gravity provides the extra pull to keep those stars whipping around so fast. So, we already know our standard models needed a massive, invisible component to explain how fast galaxies spin. But the mystery we're exploring today is even more peculiar. It's about which way they spin. When everything forms from a single, collapsing cloud, you'd expect all the parts to spin in harmony, like water all draining down a sink in the same direction. This is why the vast majority of galaxies do exhibit orderly, consistent rotation. Astronomers can measure this spin direction by carefully analyzing the light from stars and gas using the Doppler effect. As one side of a galaxy spins toward us, its light is slightly shifted toward the blue end of the spectrum. The side spinning away has its light shifted to red. By mapping these shifts across an entire galaxy, we can create a detailed chart of its motion. It's a meticulous process, but it provides a clear picture of a galaxy's rotational signature. This established framework of gravitational collapse and angular momentum makes the discovery of a galaxy spinning the wrong way so profoundly puzzling. It's as if you dropped that spinning pizza dough and it landed on the counter spinning in the complete opposite direction. It shouldn't happen according to our basic rules, and yet, out in the depths of space, it unmistakably does. This foundational puzzle sets the stage for our entire investigation, forcing us to ask what incredible forces could possibly overwrite a galaxy's original spin and impose a new direction upon it. The journey to unravel this cosmic conundrum didn't begin with modern supercomputers or space telescopes, but in the patient, meticulous work of astronomers peering through ground-based telescopes decades ago. Long before we had detailed maps of dark matter, these early observers were simply trying to catalog the heavens, to understand the basic forms and behaviors of the nebulous objects they called island universes. It was during these foundational surveys that the first hints of something unusual emerged. Astronomers noticed that while most spiral galaxies exhibited a beautiful, logical symmetry in their rotation, a handful stood out as oddities. Their spiral arms seemed to twist in a way that suggested a spin direction contrary to what was expected, almost as if nature had absent-mindedly wound a clock backward. These were more than just curiosities. They were the first whispers of a mystery that would only grow deeper with time. The mid-20th century marked a pivotal turning point, not just in detecting these anomalies, but in fundamentally reshaping our entire understanding of galactic mechanics. This was largely thanks to the pioneering work of astronomer Vera Rubin and her colleagues. While studying the rotation curves of galaxies' graphs that plot the orbital speed of stars against their distance from the galactic center, Rubin made a stunning discovery. She found that stars at the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity and the visible mass of stars and gas, those outer stars should have been slowing down, drifting away into the void. The fact that they weren't could only mean one thing: something invisible and massively powerful was holding them in place, providing the extra gravitational glue. This was the revolutionary evidence for dark matter, a discovery that forever changed cosmology. Yet, woven into this same data was another, quieter surprise. As researchers compiled these rotation curves for hundreds of galaxies, a few refused to follow the script, For the vast majority, the Doppler shift measurements, where light blue shifts on the side spinning toward us and red shifts on the side spinning away, painted a clear and consistent picture of motion. But for a small fraction of galaxies, the picture was confusing, even contradictory. The data indicated spin directions that seemed inverted or misaligned. Imagine listening to a symphony and hearing a single instrument playing a melody entirely out of key and in the wrong tempo. That was the jarring effect these galactic outliers had on the emerging model of the universe. They spun clockwise when the models predicted counterclockwise, or their outer halo of stars seemed to rotate in opposition to the inner disk. These initial discoveries did more than just puzzle researchers. They actively challenged the prevailing notion that galaxy formation was a straightforward, isolated process. If a galaxy's spin is imprinted at birth from the rotation of its primordial gas cloud, how could it later decide to spin the other way? The very presence of these cosmic rebels suggested that our understanding was incomplete. Perhaps galaxy formation wasn't always a serene, isolated collapse. Maybe violent external influences, a catastrophic collision, a close gravitational encounter with another galaxy, or the accretion of foreign material, could fundamentally rewrite a galaxy's rotational history long after its birth. These anomalous galaxies became more than just errors in the data. They became compelling clues, sparking decades of dedicated investigation into the dynamic and sometimes turbulent lives of galaxies, forcing science to look beyond simple models and consider a far more complex and interactive cosmic story. But to truly grasp how this invisible force might be responsible for such a dramatic reversal of spin, we need to visualize the dark matter halo itself. Picture a galaxy not as a flat disk of stars, but as a colossal, spherical cloud of unseen matter that extends far beyond the visible edge, like a king's crown that is vastly larger than the king himself. This immense halo provides the gravitational scaffolding upon which the entire luminous galaxy is built. The ordinary matter, the stars and gas we can actually see, simply sinks to the center of this much larger dark matter gravitational well, and it's the rotation of this dark matter core that primarily dictates the spin of everything within it. The entire system is governed by this deep, invisible anchor. Now, our standard models often assume these dark matter halos are smooth and symmetrical, like a perfectly rounded ball. But what if they aren't? What if, during the chaotic process of formation, a dark matter halo develops in a lopsided way with a denser, heavier region on one side? This irregularity, this gravitational imbalance, could potentially torque the entire system as it forms, setting the newborn galaxy spinning on an unexpected axis or even in an unexpected direction from the very beginning. It's a concept that turns a fundamental assumption on its head, suggesting that the seeds for these rotational mysteries might have been planted in the dark matter distribution billions of years before the first star even ignited. Furthermore, the interaction between these halos could be a primary culprit. Galaxies are not isolated islands. They exist in a vast cosmic web, constantly feeling the gravitational tug of their neighbors. When two galaxies pass near each other, their extensive dark matter halos are the first things to interact, long before their stars ever come close. This gravitational dance between two invisible giants can create immense tidal forces. Think of it like two dancers spinning around each other, their outstretched arms pulling and twisting each other's bodies. The dark matter halo of one galaxy could exert a powerful torque on the other, effectively grabbing its spin axis and wrenching it into a new orientation. In a particularly dramatic encounter, this could even flip the rotation of the galactic disk, leaving us with a galaxy that appears to be spinning backward compared to its original state. This leads us to an even more profound and speculative possibility. that we might not fully understand the nature of dark matter itself. The prevailing model treats dark matter as cold and collisionless, meaning its particles move slowly and mostly pass right through each other and regular matter without interaction. But what if dark matter has properties we haven't yet accounted for? Some theoretical physicists explore models where dark matter particles can interact with each other through a new, unknown force, creating a kind of dark matter fluid dynamics that could influence galactic rotation in complex ways. Or perhaps dark matter can clump together more than we think, forming dense structures within the halo that exert a more localized and powerful gravitational influence, like hidden rocks in a stream altering the current's flow. If any of these alternative ideas hold water, then the strange rotations we observe wouldn't be mere anomalies. They would be crucial clues, the first visible hints pointing us toward a deeper and richer understanding of the universe's most dominant but elusive substance. While the hidden hand of dark matter offers a compelling theoretical framework, there is a far more visceral and observable process that can violently rewrite a galaxy's rotational destiny: the colossal, slow-motion crash of a galactic merger. To understand how this works, we need to shift our perspective from a galaxy as a solitary island to seeing it as a participant in a dynamic, gravitational ecosystem, where close encounters can lead to cosmic rearrangements on an unimaginable scale. These aren't quick, explosive events, but breathtakingly slow dances of destruction and creation that unfold over hundreds of millions of years, fundamentally reshaping everything they touch. Imagine two vast spiral galaxies, each with its own distinct rotation, charting a course through the void on a fateful collision trajectory. As they begin to feel each other's gravitational pull, the first things to be affected are their vast halos of dark matter, those immense but invisible spheres that envelop each galaxy. This interaction acts like a gravitational brake, but it's anything but smooth. The mutual tug warps their shapes, stretching them like taffy, and pulling long, luminous tails of stars and gas out into space tidal tails that are the classic signature of a galactic interaction. It's during this gravitational wrestling match that angular momentum, the conserved quantity that defines a galaxy's spin, can be dramatically transferred. If a smaller satellite galaxy comes in at just the right angle, it can act like a cosmic cue ball, striking the larger galaxy and imparting a fresh dose of rotational energy in a completely new direction. This isn't just a gentle nudge, it's a fundamental rewriting of the galaxy's rotational script, a new chapter of motion imposed by a violent encounter. We don't have to just imagine this process, we can see it happening in glorious detail. A prime example is the famous pair known as the Antennae galaxies, located about 45 million light-years away. In stunning images from the Hubble Space Telescope, we see two spiral galaxies locked in a violent embrace. Their classic spiral structures are already shredded and distorted, and two massive, curved tails of material, the antennae that give them their name, arc out into space, flung there by immense tidal forces. This system is a cosmic laboratory, showing us the intermediate stage of a merger in progress. Computer simulations that model the physics of such collisions can take the initial conditions of two separate galaxies and accurately reproduce the very structures we see in the antennae, including those iconic tails. These models show that the final product of this merger will be a completely new type of galaxy, an elliptical galaxy, whose stars will orbit in a far more chaotic and random pattern, their original orderly spins erased forever by the violence of the collision. However, while mergers provide a powerful and elegant explanation for many cases of Chinese letter rotation, the cosmic puzzle is never quite that simple. This theory hits a significant snag when we discover galaxies spinning the wrong way in perfect isolation, far from any neighbors that could have recently disturbed them. If there's no evidence of a recent collision, no telltale tidal tails or distorted shapes, then we must look for other explanations. Perhaps the merger happened so long ago, billions of years in the past, that the galaxy has had time to settle back into a relaxed state, its violent history hidden beneath a serene exterior, with only its peculiar spin remaining as a silent witness to the ancient catastrophe. Or maybe the process was more subtle, not a direct collision but a gradual, stealthy accretion of gas and small satellite galaxies over eons, each adding a tiny bit of off-axis momentum that, bit by bit, slowly steered the galaxy's rotation in a new direction. The merger theory is undoubtedly a key player in this mystery, providing a dramatic and well-supported mechanism, but the presence of isolated outliers reminds us that the universe often has more than one way to achieve a surprising result. But the gravitational drama of the cosmos isn't limited to direct, head-on collisions. A far more subtle, yet equally powerful, cosmic force can also sculpt and reshape a galaxy's spin over immense timescales, the relentless pull of tidal forces. Think of our own moon's gentle but persistent tug on Earth's oceans, creating the daily rhythm of high and low tides. Now magnify that concept to a truly galactic scale. When a massive object like another large galaxy or an entire galaxy cluster passes relatively nearby, its immense gravitational field doesn't just pull uniformly, it creates a tidal force. This means the pull on the side of the galaxy closest to the passer-by is much stronger than the pull on the far side. This difference in force, this gravitational gradient, doesn't just attract the galaxy, it stretches it, warping its shape and, crucially, exerting a torque that can literally twist its rotation. This process is less like a catastrophic car crash and more like a slow, gravitational massage that gradually kneads a galaxy into a new configuration. Over hundreds of millions of years, a close but not catastrophic encounter can impart enough angular momentum to alter the spin axis of a galactic disk or, in some extreme cases, gradually break its original rotation and set it spinning in a new direction. The key here is the sheer scale of time involved. What seems like a gentle nudge on a cosmic time frame can have revolutionary consequences for the galaxy's long-term evolution. Advanced computer simulations are indispensable for modeling these complex interactions, allowing astronomers to fast forward through eons and witness the outcomes. These virtual experiments confirm that while such transformative flybys are rare in the lifetime of any single galaxy, they do happen, and they leave behind unmistakable and lasting fingerprints on the galactic kinematics, the very patterns of motion for its stars and gas. We find compelling observational support for this theory when we zoom out and look at the broader environment of galaxies, particularly within dense clusters and dynamic groups. In these crowded cosmic neighborhoods, galaxies are not isolated islands but social entities, constantly influencing one another. Astronomers have mapped the spin directions of galaxies within these clusters and found something telling. They often show signs of coordination. In some clusters, the spins of member galaxies appear to be aligned with each other, as if they were all set spinning by the same large-scale tidal field, perhaps the gravitational influence of the cluster's core itself. In other groups, we see the opposite, a clear misalignment where galaxies seem to be spinning every which way, likely the chaotic result of numerous past gravitational interactions within the group. This correlation between a galaxy's rotational state and its environment is a powerful clue. It strongly suggests that a galaxy's spin is not solely determined by its initial conditions at birth, but is also a product of its life story, a narrative written by the gravitational influences of everything that has passed it by over the last 13 billion years. Now, to truly appreciate the depth of this puzzle, we have to move beyond the idea of a galaxy as a simple, single-spinning disk and consider an even more baffling configuration. A galaxy with not one, but two distinct disks of stars, each spinning in direct opposition to the other. This isn't just a slight anomaly, it's a cosmic contradiction, a system where the very definition of forward and backward loses all meaning. Imagine a massive whirlpool where the water at the center is spinning clockwise, but the outer rim is forcefully churning counterclockwise. This defies our basic intuition about how rotating systems behave, and yet, in the case of certain galaxies, this is precisely what astronomers have found. The existence of these counter-rotating disks presents a direct and profound challenge to the simplest models of galaxy formation, which suggest that a galaxy should coalesce from a single, collapsing cloud of gas with one unified direction of spin. For a galaxy to develop these opposing rotations, its history must be far more complex and eventful. The most widely accepted explanation involves a process called accretion, the gradual gathering of material from outside. Picture a large spiral galaxy peacefully spinning in one direction for billions of years. Then, from deep space, a smaller satellite galaxy or a massive cloud of intergalactic gas drifts into its gravitational sphere of influence. If this incoming material happens to be orbiting in the opposite direction, perhaps because it originated from a different part of the cosmic web with its own unique angular momentum, it can be slowly drawn in and absorbed. Over immense timescales, this new, contrary material settles into a new disk or a distinct component within the existing galaxy, creating a layered structure with two populations of stars moving in direct opposition. It's a testament to the fact that galaxies are not closed, isolated systems. They are open to influence, constantly feeding on and incorporating their surroundings, with each new meal potentially altering their fundamental dynamics. A classic and deeply studied example of this phenomenon is the galaxy known as NGC 4550, located in the Virgo cluster. Through detailed spectroscopic observations, astronomers made the astonishing discovery that this seemingly ordinary lenticular galaxy is actually composed of two separate, interwoven disks of stars. One disk rotates in one direction while the other, equally substantial disk, rotates in the exact opposite direction. It's as if two completely separate galaxies, each with their own spin signature, decided to merge into one but never reconciled their differences. The stars in these two disks are even of different ages and compositions, telling a clear story of two separate origins. This isn't a minor feature. Roughly half of the stars in this galaxy are part of the counter-rotating population. Explaining how such a precise and balanced opposition formed requires a detailed and violent history, likely involving the capture and complete assimilation of a smaller galaxy that was rich in gas and was orbiting on a retrograde path relative to its larger host. The stability of this configuration over billions of years is itself a marvel of cosmic physics. Cases like NGC 4550 force us to abandon any notion of galaxies as monolithic, unchanging sculptures. Instead, we must see them as dynamic and ever-evolving systems, each with a rich and layered biography written in the motions of its stars. These counter-rotating disks are like geological strata in a rock formation, each layer preserving a record of a different era and a different event in the galaxy's past. They are the ultimate evidence that a galaxy's present state is only the latest chapter in a long history of interactions, mergers, and acquisitions. This complexity pushes our telescopes and our models to their absolute limits. Even with our most powerful instruments, deciphering the full three-dimensional motion of stars in a distant galaxy is an enormous challenge, often leaving us with tantalizing clues rather than complete answers. These galactic oddities, spinning in perfect contradiction, stand as humbling reminders that for all we have learned, the universe still holds profound mysteries about how its largest structures live and evolve. Yet for all their breathtaking power, our greatest observatories still face fundamental barriers that prevent them from giving us the full, three-dimensional picture we desperately need. The Hubble and James Webb Space Telescopes have revolutionized our view of the cosmos, delivering images of stunning clarity and depth, but they are ultimately bound by the unyielding laws of physics and the vast distances they strive to bridge. One of the most significant challenges is the simple fact of perspective. When we gaze at a distant galaxy, we are seeing a flat, two-dimensional projection on the sky. We have no direct, overhead view. This makes determining the true orientation and motion of that galaxy an exercise in sophisticated guesswork. It's like trying to understand the exact spin of a distant carousel when you can only see it from the side. You might see it moving, but is it spinning toward you or away from you? Is it tilted? Without that third dimension of depth, our measurements of a galaxy's rotation are inherently incomplete and open to interpretation. Astronomers must rely on complex models and statistical methods to infer the true three-dimensional motions from the two-dimensional data we can collect, a process that inevitably introduces uncertainty and leaves room for debate. Adding to this challenge is the sheer vastness of space itself. The galaxies we study are so incredibly distant that their light has been traveling for millions, even billions, of years just to reach our lenses. Over these cosmic distances, even the most minute observational errors are magnified. The faint, redshifted light that tells us a galaxy is spinning away from us can be easily contaminated or obscured. Interstellar dust, both within our own galaxy and within the one we're observing, can absorb and scatter this crucial light, effectively hiding the true motion from our view. It acts like a faint cosmic fog, dimming the signals we need and forcing us to make corrections that, while scientifically rigorous, still add another layer of potential error to our calculations. Furthermore, the immense distance means we are often looking at a galaxy's past, not its present. We are seeing it as it was when the light left it, a fossil record of its rotation from eons ago. This makes it incredibly difficult to connect what we see to the galaxy's current state, or to understand the real-time dynamics of its evolution. We are piecing together a story from scattered, ancient clues, and some pages of that story are inevitably missing or faded. These limitations are not a failure of our technology, but a reflection of its current frontier. They define the very boundary between what we know and what we have yet to discover. The persistent mystery of galaxies that spin the wrong way is a direct consequence of these observational walls. It's a humbling reminder that for all our intellectual and engineering prowess, we are still peering at the universe through a keyhole, catching tantalizing glimpses of a reality that is far more complex and dynamic than we can currently fully grasp. This is why the astronomical community looks with such anticipation to the next generation of telescopes instruments designed not just to see farther, but to see smarter, with the resolution and sensitivity needed to finally turn these two-dimensional hints into a definitive, three-dimensional understanding of galactic life. Faced with the observational limitations of even our most powerful telescopes, astronomers have turned to a different kind of instrument to unravel this cosmic mystery, the supercomputer. By building intricate virtual universes from the ground up, they can run experiments that would be impossible in the real world, testing countless scenarios to see which ones might produce Chinese letter spinning galaxies we actually see. This is the realm of computational astrophysics, a field where code and processing power become a laboratory for the cosmos. The goal is breathtakingly ambitious: to simulate the entire 13.8 billion-year history of the universe, from the smooth soup of the primordial Big Bang to the intricate web of galaxies we see today, and to see if that virtual history naturally gives birth to the same oddities that puzzle us in our own night sky. Leading this charge are monumental simulation projects with names like Illustris TNG, Eagle, and Magneticum. These are not simple video game recreations. They are some of the most complex software ever written, incorporating the known laws of physics on a truly epic scale. They begin with a volume of space, often hundreds of millions of light years across, populated with a grid of dark matter particles based on the initial conditions we've measured from the cosmic microwave background. Then they let gravity take over. As the simulation runs, the dark matter begins to clump, forming the invisible scaffolding of the cosmic web. Ordinary matter, represented as gas particles, follows this gravitational blueprint, flowing into the dark matter halos, cooling, and eventually forming stars and galaxies. But the real magic and the key to solving the rotation mystery lies in what the simulators call subgrid physics. This is the code that accounts for phenomena too small or complex to be directly simulated, like the explosive feedback from supernova or the powerful jets erupting from supermassive black holes. These energetic events can blast gas out of a galaxy, effectively robbing it of angular momentum and potentially altering its spin in profound ways. The results have been both illuminating and humbling. In many cases, these virtual universes do indeed generate galaxies that spin the wrong way. The simulations show that mergers are a primary engine for this phenomenon, with the angle and mass ratio of the colliding galaxies dictating the final rotational outcome. They also demonstrate how a galaxy can gradually have its spin torqued and twisted by the constant, subtle gravitational tugs from the cosmic filaments of dark matter that make up the large-scale structure of the universe. In one particularly telling experiment, researchers might watch as a virtual galaxy spinning peacefully for billions of years is struck by a smaller companion. The simulation tracks how tidal forces strip stars and gas, and how the transfer of angular momentum can indeed flip the spin axis of the larger galaxy, leaving behind a perfect digital analog to the real-world anomalies we observe. This provides powerful, albeit indirect, evidence that the merger theory is on the right track. Yet for all their success, a persistent gap remains between the simulated universe and the real one. The galaxies produced in even the best simulations still don't perfectly match the statistical distribution and specific properties of Chinese letter spinning galaxies we find in our surveys. Some simulations might produce too few of them, others might create them but with the wrong kinds of stars or gas content. This discrepancy is a crucial clue in itself. It tells us that while we have captured the broad strokes of galaxy evolution, our models are still missing something. Perhaps our understanding of dark matter-particle interactions is too simplistic, or maybe the feedback from black holes is even more powerful and complex than we've coded it to be. It could be that magnetic fields, which are incredibly difficult to simulate over such vast scales, play a more significant role in shaping galactic rotation than we currently appreciate. Every mismatch between the virtual cosmos and the real one is not a failure, but a signpost pointing toward new physics, driving a continuous cycle of refinement where each new observational discovery helps programmers improve their code, inching us ever closer to a true digital twin of our perplexing and magnificent universe. While we often picture galaxies as being governed solely by the immense force of gravity, there's another, far more subtle player weaving its way through the cosmic fabric: magnetism. It's easy to overlook these fields. Their strength is minuscule compared to gravity, often 1,000,000 times weaker or more. But what they lack in raw power, they make up for in pervasive influence, acting like an invisible cosmic glue that can gently but persistently guide the flow of matter over astronomical timescales. These magnetic fields don't originate from giant bar magnets in space. They are born from dynamo action, a process where the motion of conductive plasma, the ionized gas that fills galaxies, can amplify a tiny seed field into a large-scale, ordered structure. It's a self-reinforcing cycle. The rotation of the galaxy churns the plasma, and that motion strengthens the magnetic field, which in turn can influence how that plasma moves. This magnetic influence primarily works its magic on the gas within a galaxy, the raw material for future stars. As vast clouds of this gas collapse to form new stellar nurseries, even a weak magnetic field can create resistance, like a swimmer trying to move through water thickened with invisible threads. This magnetic drag can act as a brake on certain motions or, conversely, can channel flows along specific magnetic field lines. Over hundreds of millions of years, this persistent tug can transfer angular momentum, effectively acting as a subtle torque that could gradually alter the spin of the entire gas disk. It's a slow-motion process, a gentle nudge compared to the violent shove of a galactic merger, but given enough time, these tiny nudges can steer the evolution of a galaxy's rotation in significant ways. This is especially true in the dense, gas-rich regions where star formation is rampant, as the energy from newborn stars and dying supernova can further tangle and amplify these magnetic fields, increasing their influence. We are not simply theorizing about these hidden forces, we can actually map them. This is the incredible capability of modern radio astronomy. Telescopes like the Very Large Array in New Mexico or the Future Square Kilometer Array don't just see in radio waves, they can detect the polarization of that light. As radio waves travel through space, their alignment can be rotated by passing through magnetized plasma, a phenomenon known as Faraday rotation. By meticulously measuring this effect from countless distant sources, astronomers can painstakingly reconstruct the three-dimensional structure of magnetic fields within entire galaxies. The results are stunning. We've discovered that some spiral galaxies possess magnetic fields that beautifully trace their spiral arms, running along the vast lanes of gas and dust for tens of thousands of light years. In others, the fields are more chaotic, a turbulent mess left over from a past collision or a burst of intense star formation. The very existence of these large-scale, ordered fields is proof that magnetism is a fundamental component of the galactic ecosystem, not just a minor footnote. So, could these fields be the sole explanation for a galaxy spinning the wrong way? Probably not. Gravity, from both visible matter and dark matter, remains the undisputed heavyweight champion in determining a galaxy's bulk motion. A magnetic field is unlikely to completely reverse the spin of an entire galaxy on its own. But what it can do is act as a crucial modifier, a complicating factor that can amplify or dampen the effects of other processes. Imagine a galaxy that has had its spin slightly altered by a minor gravitational encounter. A well-ordered magnetic field could then act to reinforce that new direction, helping to settle the galaxy into its new rotational state. Or, in the case of a counter-rotating disk, magnetism could help shepherd accreted gas with opposite angular momentum into a stable, coherent structure, preventing it from just scattering and mixing away. It's the difference between a single force acting alone and an entire symphony of forces working in concert. The gravitational pull of dark matter sets the stage, the hydrodynamic flow of gas writes the melody, and the magnetic field provides the subtle, underlying harmony that ties everything together, reminding us that to understand the full, complex story of why a galaxy spins the way it does, we must listen to every instrument in the cosmic orchestra. Just when we thought the mystery of galactic spins was confined to the galaxies themselves, a new layer of complexity emerges from their smallest companions, forcing us to widen our gaze to the entire gravitational ecosystem a galaxy commands. For every majestic spiral like our Milky Way, there is often an entourage of smaller satellite galaxies, tiny celestial dwarfs held in orbit by its immense gravitational pull. These aren't merely decorative, they are cosmic historians, their motions preserving a record of the larger system's formation and evolution. For a long time, the simplest assumption was that these satellites would orbit in a random, chaotic swarm around their host, like bees buzzing around a hive. But recent, painstaking observations have upended that expectation, revealing patterns in their orbits that are as surprising as they are difficult to explain, directly challenging our models of how cosmic structures grow. One of the most startling discoveries is that many of these satellite galaxies do not swarm randomly at all. Instead, they seem to prefer orbiting in a single, vast, and incredibly thin plane, a great circle around their host galaxy, almost like the rings of Saturn but on a million-fold larger scale. Even more perplexing is how this plane of satellites often aligns with the host galaxy's own spin. It's as if the entire system, from the central spiral down to its tiniest orbiting dwarf, is spinning in a coordinated dance. This is deeply puzzling because our leading model of the universe, the lambda cold dark matter model, predicts that satellites should be accreted from all directions, forming a roughly spherical cloud. The existence of these thin, rotating planes of satellites suggests that the process of galaxy formation is far more orderly and structured than we thought, or that some unknown physical process is organizing these small galaxies long after they are captured. But the plot thickens considerably when we look at the specific relationship between a satellite's orbit and its host's rotation. In some systems, the alignment is so precise it defies belief. Perhaps the most famous example is our own Milky Way. Its most significant satellites, the Large and Small Magellanic Clouds, along with a dozen other dwarf galaxies, are not scattered randomly across the sky. They are arranged in a remarkable, narrow plane that is almost perpendicular to the disk of our galaxy. This means their orbital path is slicing directly through the plane of our spiral, a configuration that is incredibly difficult to achieve and maintain through random chance alone. It suggests that the forces which shape the rotation of the Milky Way itself also dictated the specific orbital paths of its entourage, locking them into this precise and seemingly unnatural alignment. Explaining this requires us to consider the entire life history of a galaxy, not just its current state. One compelling theory points to the role of cosmic filaments, the immense threads of dark matter that make up the large-scale structure of the universe. A large galaxy like the Milky Way may have formed at the intersection of two such filaments. As it grew, it drew in gas and smaller protogalaxies that were flowing along these specific dark matter highways. This process would have naturally funneled incoming material, including future satellite galaxies, along a preferred direction, imprinting a specific orbital alignment that has persisted for billions of years. It's a galactic version of destiny, where the path you're born on determines your ultimate trajectory. Another possibility involves tidal locking, where the relentless gravitational pull of the host galaxy over eons gradually synchronizes the orbits of its satellites, shepherding them into a common plane, much like the moons of Jupiter are locked into orderly orbits around their giant planet. The implications of these satellite studies ripple far beyond our local group. They suggest that a galaxy's rotation is not an isolated feature. It is intrinsically linked to the architecture of its immediate surroundings, a product of the hierarchical way the universe builds structures. The spin of the central galaxy and the orbital alignment of its satellites are two sides of the same coin, both forged by the same primordial conditions and the same history of accretion. This adds a profound new layer of complexity to the mystery of Chinese letter rotation. If a large galaxy were to have its spin flipped by a merger, what does that do to its satellites? Would their orbital plane be dragged into a new alignment, or would it stubbornly hold onto the memory of the galaxy's original spin direction? These are questions we are only just beginning to ask. This is where monumental projects like the Gaia Space Observatory become absolutely revolutionary. Gaia is not just mapping the stars in our galaxy, it is charting their motions in 3 dimensions with unprecedented precision. This data allows astronomers to not only confirm the precise orbits of satellite galaxies around the Milky Way, but to trace their paths backward in time, effectively rewinding the cosmic film to see where they came from. Early results from Gaia have already provided stunning evidence that many of these satellites are moving together in coherent streams, the remnants of smaller galaxies that were torn apart by the Milky Way's gravity eons ago. Each of these stellar streams is like a ghostly arrow pointing back to a single, ancient accretion event. By connecting the current orbital alignments of satellites to these past events, Gaia provides the crucial forensic evidence needed to test our theories. It allows us to move from simply observing that satellites have aligned orbits to understanding exactly how and when those alignments were established, turning a baffling cosmic pattern into a readable history book that details the dynamic and often violent process of galactic growth. The silent, orderly dance of these satellite galaxies is no longer just a curiosity. It is a critical clue written in the language of motion that is guiding us toward a deeper understanding of the forces that sculpt not just individual galaxies, but their entire cosmic neighborhoods. But the gravitational influence of a galaxy doesn't end with its visible stars or even its dark matter halo. At the very heart of most large galaxies lies an object of such immense density and power that it can orchestrate events on a truly galactic scale, a supermassive black hole. These cosmic behemoths, containing millions or even billions of times the mass of our Sun, are often portrayed as passive, insatiable monsters simply consuming anything that ventures too close. However, the reality is far more dynamic and influential. While their gravitational pull is unquestionably dominant in their immediate vicinity, it's their active phases periods when they are actively feeding on surrounding gas and dust that can unleash forces powerful enough to potentially rewrite the rotational destiny of their entire host galaxy. This process transforms the black hole from a silent anchor into a brilliant, energetic engine, and it is through this furious activity that it can impart its will upon the galactic disk. When a supermassive black hole is actively accreting material, it doesn't do so quietly. As matter spirals inward at Chinese letter relativistic speeds, it forms a superheated disk of plasma, and not all of this material crosses the event horizon. Instead, a significant fraction of it can be funneled and accelerated by the black hole's immensely powerful magnetic fields, launching twin jets of energetic particles that blast outward at nearly the speed of light, perpendicular to the accretion disk. Simultaneously, tremendous outflows of gas and radiation can erupt from the system, flooding the surrounding region with energy. This entire spectacular phenomenon is what astronomers call an active galactic nucleus, or AN. These jets and outflows can extend for tens of thousands of light years, far beyond the confines of the galactic center, and they carry with them an enormous amount of energy and momentum. This isn't a gentle process, it's a galactic-scale hurricane unleashed from the core. The impact of this energetic feedback on the galaxy's rotation is a complex ballet of physics. As these powerful outflows slam into the surrounding reservoirs of cold gas, the very fuel for future star formation, they create immense shock waves. This interaction doesn't just heat the gas, it can push it, drag it, and effectively steal its angular momentum. Think of it like a spinning ice skater suddenly throwing their arms out wide. Their rotation slows down. Now, imagine that same skater having someone else forcefully grab their arms and pull them outward. The AGN feedback acts as that external force. By injecting energy into the galactic gas, it can apply a powerful torque, potentially breaking the rotation of the inner galactic regions or even altering the spin axis over time. In extreme cases, if the outflow is asymmetric, perhaps because the accretion disk is tilted or the surrounding gas is unevenly distributed, this torque could be so forceful that it begins to counteract the galaxy's original spin, setting the stage for a reversal in certain parts of the system. It's a dramatic demonstration of how the most extreme environment in the galaxy can govern the motion of matter hundreds of light years away. We are not just theorizing about this potential, we are beginning to find compelling observational correlations that strongly suggest a link. Astronomers have identified specific galaxies where heightened AGN activity coincides with clear and puzzling kinematic anomalies. In these systems, the gas in the central regions shows motions that are misaligned or even counter-rotating compared to the broader stellar disk. This is a telltale signature of a recent, powerful injection of energy that has disturbed the settled order of the galaxy. It appears that the violent feedback from the central black hole has effectively scrambled the angular momentum of the gas, creating a localized rotational mystery right in the galaxy's core. While it may not flip the entire galaxy's spin overnight, this process demonstrates that the central engine is more than capable of causing significant and unexpected rotational changes, leaving a distinct imprint that our telescopes can detect. This connection weaves black holes directly into the grand narrative of galactic rotation mysteries. It highlights a profound concept in modern astrophysics: scale invariance. The laws of physics that operate on the smallest scales around a single black hole can have direct and dramatic consequences for the largest structures in the universe. The magnetic fields threading the accretion disk, the hydrodynamics of the inflowing gas, and the relativistic speeds of the jets, all these micro-scale phenomena can cascade outward, influencing the macro-scale rotation of an entire galaxy. It shatters the idea that a galaxy's spin is a simple, stable property determined solely by its initial conditions. Instead, it reveals a dynamic and ongoing conversation between the galaxy and its central black hole, a feedback loop where the galaxy feeds the black hole, and the black hole, in turn, responds by reshaping the galaxy that feeds it, potentially even altering its very spin. This places supermassive black holes not as passive inhabitants, but as active, powerful participants in the cosmic story, capable of steering the evolution of their galactic homes in ways we are only just beginning to comprehend. To truly grasp how a galaxy's spin could be set in motion from the very first moments of existence, we must journey back to a time before galaxies, before stars, even before atoms, to a fleeting fraction of a second after the Big Bang. This is the era of cosmic inflation, a concept so profound it reshaped our entire understanding of the universe's origins. Imagine the newborn cosmos, smaller than a single proton, undergoing an exponential, faster-than-light expansion, smoothing out and stretching the fabric of spacetime itself in an instant. This wasn't an expansion into space, it was an expansion of space, and it set the stage for everything to come. As this inflationary field decayed, it filled the universe with a hot, dense plasma, and most importantly, it imprinted upon it the tiniest of quantum fluctuations, microscopic ripples in density that would become the cosmic blueprint for all future structure. These primordial imperfections are the seeds from which galaxies would eventually grow. Where there was a slightly denser region, gravity had a bit more to work with, slowly pulling more matter in over billions of years. But this process wasn't just about building mass, it was also about imparting spin. As these nascent overdensities began to collapse under their own gravity, the slightest initial tug, a minute torque from a neighboring density fluctuation, could set the entire condensing cloud rotating. This is the principle of tidal torquing on a cosmic scale. The original quantum jitter from inflation, amplified by gravity's relentless pull, didn't just determine where galaxies would form, but potentially how they would spin. The initial angular momentum for an entire galaxy, a whirlpool of hundreds of billions of stars, may have been sourced from these subatomic ripples in the very first moments of time. This idea pushes the mystery of Chinese letter rotation to its absolute limits, suggesting that the spin direction of a galaxy might not be a random outcome of local conditions, but a fate written into the cosmos at its birth. Some theoretical cosmologists take this a step further, proposing that the specific patterns of inflation could have created large-scale correlations in the spin axes of galaxies. In certain models, the same quantum fluctuations that determine density might also have imprinted a preferred handedness, a subtle bias in the rotation of these primordial clouds. If this is true, then the anomalous galaxies we see today spinning contrary to their neighbors might not be rebels at all. They could simply be following a script written in the first trillionth of a second of the universe, their unusual spin a direct consequence of the unique inflationary conditions in their particular patch of the cosmos. Testing this breathtaking idea is one of the greatest challenges in modern cosmology. We cannot go back to witness inflation, but we can look for its fossilized imprint on the oldest light in the universe, the cosmic microwave background. This afterglow from the Big Bang, which fills the entire sky, is a snapshot of the universe when it was just 380,000 years old. By mapping the minute temperature variations and, more importantly, the polarization patterns in this light with exquisite precision, missions like the Planck satellite have been hunting for indirect evidence of these primordial gravitational waves and the specific type of inflation that could have caused them. The patterns of polarization, in particular, could theoretically hold clues about the universe's initial conditions, including those that might have seeded rotation. While no definitive signal linking the CBM to galactic spins has been found yet, the very possibility fuels a fascinating line of inquiry, connecting the largest-scale structures we see today to the most fundamental physics that operated at the smallest scales imaginable. It's a humbling reminder that the answer to why a galaxy spins the wrong way might not be found by looking at the galaxy itself, but by studying the faint, cold glow of the infant universe, searching for the faintest of whispers from the dawn of time. Yet, even as we search for answers in the depths of space and the earliest moments of time, we must also contend with a far more immediate and humbling challenge: the inherent limitations of our own perspective. The story of galactic rotation isn't just written in the stars, it's filtered through the lens of our instruments and our own earthly viewpoint, a process fraught with potential for misinterpretation. One of the most significant hurdles we face is a simple trick of geometry known as the projection effect. When we observe a distant galaxy, we are seeing a flat, two-dimensional image projected against the celestial sphere. We have no true depth perception, no ability to see it from the top or the side. This means a galaxy's inclination, the angle at which its disk is tilted relative to our line of sight, becomes the single most important factor in determining what we think we see, and it can easily lead us astray. Imagine holding a spinning dinner plate. If you look at it directly face on, its rotation is obvious. You can clearly see it spinning clockwise or counterclockwise. But if you tilt the plate until you're seeing it almost perfectly edge-on, discerning its spin direction becomes nearly impossible. This is precisely the challenge astronomers face. A galaxy that is tilted away from us might appear to have spiral arms that suggest one direction of rotation, when in reality, its true motion could be entirely different. What looks like a galaxy spinning the wrong way could, in some cases, simply be a galaxy that is tilted at an odd angle, creating an optical illusion that our telescopes struggle to penetrate. Determining the true inclination requires careful measurement of the galaxy's apparent ellipticity, how squashed it looks, but even this is an imperfect science, as galaxies are not perfect, flat disks, and can have warped or irregular shapes that further confuse the issue. This fundamental ambiguity means that a certain number of the rotational anomalies in our catalogues are almost certainly not real physical phenomena, but mere mirages created by our unfortunate and unchangeable vantage point. Compounding this problem of perspective is the issue of selection bias in our large-scale sky surveys. Telescopes like the Sloan Digital Sky Survey have mapped millions of galaxies, but they don't see everything equally. These instruments have specific limits on their sensitivity and resolution. They are better at detecting brighter, larger, or more nearby galaxies, which means our sample of well-studied rotating systems is not a perfect representative slice of the galactic population. It's a skewed dataset. For instance, a galaxy with a faint, counter-rotating outer disk might be completely missed if the survey isn't sensitive enough to detect its faintest stars. Alternatively, a survey might preferentially detect galaxies that are face-on to us because they appear larger and brighter, while edge-on galaxies, which are crucial for accurate rotation curve measurements because their motion is more directly along our line of sight, are harder to study in detail. This means we could be systematically overcounting certain types of rotational configurations while missing others entirely, creating a statistical picture that doesn't fully reflect the true diversity of the cosmos. The human element also introduces its own subtle biases. When astronomers develop automated algorithms to classify galaxy rotations, they must first train these algorithms using data that has already been classified by people. If the human classifiers have an unconscious tendency to interpret ambiguous cases in a particular way, that bias gets baked into the machine learning model, which then goes on to perpetuate and amplify that same bias across the entire dataset. It's a modern-day version of a self-fulfilling prophecy, where we might be finding more of what we already expect to see, simply because our tools are designed to look for it. This is why the astronomical community places such a strong emphasis on developing robust, independent methods for cross-validating observations. By using different telescopes operating at various wavelengths, optical, radio, infrared, we can triangulate the truth. A rotation measured by the Doppler shift of stars should, in principle, match the rotation measured by the motion of hydrogen gas clouds in radio waves. If they disagree, it's a huge red flag that either our measurement or our interpretation is flawed. Acknowledging these biases isn't an admission of failure, it's a fundamental part of the scientific process. It represents a mature understanding that raw data is never perfectly pure. It must be carefully cleaned, calibrated, and scrutinized before it can be trusted. The relentless effort to filter out these observational artifacts is what separates genuine cosmic mysteries from mere measurement errors. It refines our quest, forcing us to ask sharper questions. Instead of, why do so many galaxies spin the wrong way? We can ask a more precise and powerful question. After accounting for all known biases, which of these anomalous rotations are truly real, and what do they alone tell us about the limits of our physics? This painstaking work of error checking and statistical correction is the unglamorous backbone of discovery. ensuring that when we finally point to a galaxy and declare its rotation a profound enigma, we can do so with the utmost confidence that we are staring at a real puzzle of the universe and not just a trick of the light. Given the profound challenges that dark matter presents, it's only natural that some scientists have chosen to walk a radically different path, questioning not the existence of an invisible substance, but the very laws of gravity themselves. This bold approach centers on a theory known as modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the early 1980s, MND offers a fascinatingly simple premise. What if we don't need dark matter at all? What if instead our understanding of gravity is simply incomplete, especially in the extremely weak gravitational fields found at the outskirts of galaxies? This idea suggests that Newton's famous laws, which work perfectly well in our solar system, might need a slight adjustment to account for the strange motions we see on galactic scales. The core principle of MND is elegantly straightforward. It proposes a new constant of nature, a tiny acceleration threshold. Above this threshold, gravity behaves exactly as Newton and Einstein said it would. But below it, in regions where gravitational pull becomes incredibly faint, the force of gravity strengthens, becoming inversely proportional to the distance rather than the square of the distance. This single tweak to the mathematical formula has a dramatic effect. It successfully explains the flat rotation curves of galaxies without invoking any unseen dark matter. The stars on the outskirts are moving faster because gravity itself is stronger out there than our standard models predict, pulling them along and preventing them from drifting away. For a lone, isolated galaxy, MND is remarkably effective, often providing a more precise fit to the rotation curve data than some generic dark matter models. This leads to a compelling implication for our central mystery. If MND is correct, then the rotation of a galaxy isn't dictated by the hidden gravitational hand of an invisible halo, but by the inherent behavior of gravity itself in the realm of the very faint. This could naturally lead to a wider variety of rotational outcomes. The spin of a galaxy in a MONDIAN universe might be more sensitive to its initial conditions, its history of interactions, or the distribution of its visible mass alone. Certain anomalous rotations that are deeply puzzling in the dark matter paradigm might find a more natural, if not immediate, explanation within this alternative framework. It's a paradigm shift that attempts to solve the puzzle not by adding a mysterious new ingredient, but by rethinking the recipe of fundamental physics. However, for all its elegance in explaining individual galaxies, MND faces a monumental challenge when it tries to scale up to the entire universe. The theory was specifically crafted to solve galactic rotation curves, and that is where its success is most notable. When applied to larger structures like massive clusters of galaxies, it begins to falter. Observations of galaxy clusters reveal two major problems. First, the observed gravitational lensing, the way these clusters bend the light from objects behind them, is far too strong to be explained by the visible matter alone, even with MND-modified gravity. The clusters simply have more gravity and thus more mass than MND can account for with the stars and gas we can see. Second, the hot, X-ray emitting gas that fills these clusters is held in place by gravity. The amount of gas and the pressure it is under indicate it is sitting in a much deeper gravitational well than MND formulas can produce without adding some form of unseen mass. These cluster-scale observations force MND proponents to reluctantly admit that some additional, unseen matter might still be needed, ironically pushing the theory back toward the very concept it sought to eliminate. The difficulties only compound when we consider the cosmos as a whole. The standard lambda-cold dark matter model, which includes both dark matter and dark energy, provides a stunningly successful framework for understanding the universe's large-scale structure, the precise patterns in the cosmic microwave background, and the accelerating expansion of the universe. MND, in its original form, has struggled to offer a complete cosmological model that can explain all these phenomena with the same consistency. While there are ongoing efforts to create relativistic extensions of MND, such as tensor vector scalar gravity, these theories often become more complex and introduce their own sets of challenges, without yet matching the comprehensive explanatory power of the prevailing model. Yet, the value of MND and other alternative theories cannot be measured solely by their ability to dethrone dark matter. Their true worth lies in their role as a necessary and vital provocateur in the scientific process. They force the mainstream community to constantly question its assumptions, to refine its models, and to seek even more robust evidence. The persistent anomalies in galactic rotation, including THOSE Chinese letter spins, serve as a constant reminder that our models are not perfect. The fact that MND can so accurately predict the rotation curves of many diverse galaxies from their visible matter alone is a tantalizing clue that we should not ignore. It suggests that there is a deep, perhaps yet to be understood connection between the distribution of visible matter and the gravitational effects we attribute to dark matter. By pushing researchers to think creatively and defend their assumptions, these alternative ideas ensure that no stone is left unturned in our quest to understand why the universe moves the way it does. They are not merely competitors in a race for a single truth. They are essential partners in a grand, collaborative effort to stress-test our understanding of reality, ensuring that when a final answer to the mystery of galactic rotation is found, it will be built upon a foundation that has been challenged, scrutinized, and proven strong enough to hold. To uncover the secrets of a galaxy's rotational past, we must learn to read the stories written in the motion of its stars, a field of detective work known as galactic archaeology. This isn't about digging up physical artifacts. It's about sifting through the cosmic genealogical records held in the positions, velocities, and chemical compositions of billions of individual suns. Every star in a galaxy is a time capsule, born at a specific moment in the galaxy's long history, and its motion through space is a direct inheritance from the conditions present at its birth. By meticulously mapping these stellar motions, astronomers can effectively rewind the cosmic clock, tracing back the evolutionary paths of stars to reconstruct the galaxy's dynamic history, including dramatic chapters where its very spin may have been thrown into chaos. The key to this historical reconstruction lies in the fact that stars of different ages behave differently. The stars in the orderly, thin disk of a spiral galaxy like our Milky Way are generally younger and rotate around the galactic center in a coherent, flat plane like a well-rehearsed ballet. They represent the galaxy's settled, modern era. In stark contrast, the stars found in the vast, spherical halo that envelops the disk are ancient relics among the first stars to ever form. Their motions are not orderly at all. They plunge around on radial, chaotic orbits, diving through the disk on random inclinations, as if remembering a time before the galaxy achieved its current, elegant rotation. This population of halo stars is a living fossil record of the galaxy's violent youth, a period of frantic assembly and gravitational turmoil. The very presence of this chaotic halo provides the first major clue that a galaxy's rotation was not always the serene dance we see today. This is where the mystery of Chinese letter rotation finds one of its most powerful lines of evidence. Imagine an astronomer discovers that a galaxy's overall disk appears to be spinning in one direction, but a specific, distinct population of stars within that disk, stars that are all the same age and chemical composition is rotating in the exact opposite direction. This is the smoking gun of a major past event. Such a counter-rotating stellar population could not have formed in place. It is a clear sign of accretion, the galactic equivalent of adoption. It tells us that these stars were born elsewhere, in a smaller satellite galaxy that had its own independent spin direction, and were then captured and assimilated by the larger host galaxy billions of years ago. The larger galaxy's gravity stripped these stars away, but it could not erase the memory of their original motion. They continue to orbit against the flow, a perpetual testament to a long-ago cosmic merger that forever changed the rotational fabric of their new home. The power of this stellar genealogy extends beyond just identifying past mergers. It can actually date them. Stars carry a built-in clock in their chemical makeup. The universe was born with only hydrogen, helium, and a trace of lithium. Every heavier element, what astronomers call metals, was forged in the nuclear furnaces of stars and scattered into space by their explosive deaths. This means that younger stars are more metal-rich than older stars. By measuring the metal content of a counter-rotating population of stars, astronomers can estimate when they formed. If they are very metal-poor, they are ancient, suggesting the merger that brought them in happened in the distant past. If they have a higher metal content, the event was more recent. This allows researchers to build a detailed timeline of a galaxy's assembly, correlating specific rotational changes with specific epochs in cosmic history. It transforms the galaxy from a static portrait into a dynamic biography, with each chapter of mergers and acquisitions leaving its unique mark on the stellar kinematics. Modern astronomical surveys have turned this painstaking work into a large-scale enterprise. Missions like the European Space Agency's Gaia spacecraft are revolutionizing the field by providing precise three-dimensional positions and velocities for over 1 billion stars in our own Milky Way. This incredible dataset is the ultimate family history book for our galaxy. By analyzing the motions of these stars, galactic archaeologists have already found compelling evidence of our own galaxy's violent past. They've identified entire streams and clusters of stars moving in unison, the ghostly remnants of smaller galaxies that were torn apart and consumed by the Milky Way long ago. Some of these stellar streams show motions that are tilted or even counter to the rotation of the main disk. These are the echoes of past collisions, events that would have sent gravitational shockwaves through our galaxy, potentially disturbing its spin and contributing to the complex rotational structure we see today. By studying our own galactic history in such intimate detail, we gain a foundational template for interpreting the stories written in the stars of distant galaxies, slowly piecing together the universal processes that can make a galaxy spin the wrong way. While the titanic forces of dark matter and the violent drama of galactic mergers work on individual systems, there exists an even more profound and pervasive influence shaping the cosmos from the largest scales imaginable: the mysterious force of dark energy. This enigmatic component, making up about 68% of the universe, doesn't pull things together like gravity. It does the exact opposite, causing the very fabric of space itself to expand at an accelerating rate. It's a background force that operates across the entire universe, and while it doesn't reach out and directly grab a galaxy to change its spin, its relentless push fundamentally alters the entire stage upon which galaxies form, evolve, and interact, indirectly writing the rules for the cosmic dance of rotation. To understand this subtle connection, we need to zoom out from individual galaxies to the grand architecture of the cosmos, known as the cosmic web. Picture the universe not as a random scatter of galaxies, but as an immense, interconnected network of vast filaments, dense knots, and enormous, empty voids. These filaments are the superhighways of dark matter and gas, along which galaxies are woven like pearls on a string. This web didn't form randomly. It grew from the tiny primordial fluctuations in the early universe, with gravity acting over billions of years to pull matter into these dense threads and clusters. The growth and stability of these filaments are absolutely crucial because they are the birthplaces and nurseries of galaxies. It is within these flowing rivers of dark matter that proto-galaxies first collapse, and it is the tidal gravitational forces from these large-scale structures that can impart the initial spin or torque on a newborn galaxy, setting it rotating for the rest of its life. This is where dark energy makes its indirect but crucial entrance. As the dominant force in the universe today, dark energy's accelerating expansion acts as a counterweight to gravity's attractive pull. In the early universe, gravity had the upper hand, allowing the cosmic web to condense and galaxies to form rapidly. But as dark energy has come to dominate, its repulsive effect has begun to suppress the formation of new large-scale structures. It makes the cosmic expansion accelerate, which stretches the space between matter, effectively diluting the density of the cosmic web and making it harder for new filaments to collapse under their own gravity. This means the growth of the cosmic web has significantly slowed down over the last several billion years. For a galaxy, this changes everything about its environment. The tidal fields, the subtle gravitational gradients that stretch and torque galaxies, are generated by the uneven distribution of matter in these filaments and clusters. If dark energy is slowing the growth and altering the shape of these large-scale structures, then it is also indirectly influencing the strength and direction of the tidal forces that can shape a galaxy's spin throughout its history. Consider a galaxy that formed early in the universe when the cosmic web was young and dynamic. It would have been subjected to strong, frequent tidal torques from rapidly collapsing filaments and nearby protogalaxies, likely resulting in a significant initial spin. Now imagine a galaxy trying to form today in a universe dominated by dark energy. The environment is far more sedate, the cosmic web is more diffuse, and the tidal forces are weaker. This late-forming galaxy might end up with a much slower rotation, or its spin axis might be determined by a different set of rules altogether, all because the background expansion rate of the universe has changed the conditions for growth. Furthermore, dark energy influences how galaxies interact with each other over cosmic time. As the expansion accelerates, it increases the physical separation between distant galaxy clusters. This makes major mergers less frequent than they were in the past, potentially making one of the primary mechanisms for dramatic spin changes, a galactic collision, a far rarer event in the future history of the universe. This vast, large-scale perspective fundamentally changes how we view the mystery of Chinese letter rotation. It tells us that a galaxy's spin is not just a local phenomenon, determined solely by its own mass and immediate neighbors. Instead, it is a property shaped by a hierarchy of influences, from the quantum seeds of inflation to the violent merger with a neighbor, all the way out to the accelerating expansion of the entire cosmos driven by dark energy. The spin of a single spiral galaxy is a product of its entire history, and that history is written on a canvas that is itself stretching and evolving. The anomalous rotations we see today could therefore be fossil records of a different cosmic era, a time when the influence of dark energy was negligible and the tidal forces of the young cosmic web were far more potent and chaotic. By studying the spins of galaxies of different ages, we might actually be able to trace the history of dark energy's influence on the universe, using galaxies themselves as cosmic chronometers measuring the evolution of the largest structures in existence. This connects the most intimate detail of a galaxy's dynamics to the grandest and most mysterious force in the cosmos, revealing a universe that is interconnected in ways we are only beginning to appreciate. For all the tantalizing clues we've gathered from computer simulations and painstaking observations, the truth is that many of the deepest secrets of galactic rotation remain frustratingly out of reach, locked away by the fundamental limitations of our current telescopes. But what if we could build a new key? This isn't a distant fantasy. It's the concrete reality taking shape in deserts and on plains across the globe, where the next generation of astronomical giants is being forged. These are not mere incremental upgrades. They are quantum leaps in engineering, instruments so powerful they promise to transform the enigmatic blurs in our current data into breathtakingly sharp, dynamic portraits of galactic life. The path to finally understanding why some galaxies spin the wrong way is being paved right now with glass, steel, and unprecedented ambition. Leading this charge is a behemoth emerging from the high desert of northern Chile, the Extremely Large Telescope, or ELT. The name is a masterpiece of understatement. Its primary mirror stretches an almost unbelievable 39 meters across, a colossal mosaic of nearly 800 individual hexagonal segments that will gather more light than all of the world's existing large telescopes combined. This immense light-gathering power is the key to its revolutionary potential. For the mystery of galactic rotation, the ELT's capabilities are nothing short of magical. It will possess the resolution to not just see a distant galaxy, but to resolve the motions of individual stars within it, even in galaxies millions of light-years away. Imagine being able to track the precise velocity of thousands of stars across a galactic disk, constructing a detailed three-dimensional map of their orbits. This would allow us to move beyond inferring a galaxy's overall spin and instead directly observe the complex kinematic tapestry within it, identifying subtle counter-rotating streams, warped disks, and the faint gravitational fingerprints of past mergers that are currently completely invisible to us. The ELT will essentially give us a time machine to witness the dynamic aftermath of galactic interactions, providing the direct evidence needed to confirm or refute the merger theory once and for all. While the ELT will dominate the optical and infrared skies, a different kind of revolutionary is rising from the quiet landscapes of South Africa and Australia. The Square Kilometre Array, or SCAR, is not a single dish but a vast network of thousands of radio antennae spread across continents, working in perfect synchrony to create a virtual telescope with a collecting area of, you guessed it, a square kilometre. Its power lies not in sharp images of stars, but in its unparalleled sensitivity to the faint radio whispers of cold hydrogen gas. This neutral hydrogen is the primordial fuel for galaxies, and it often extends far beyond the visible starlight, tracing the outermost reaches of a galaxy's gravitational influence. The SKA will map the rotation of this faint gas in exquisite detail for millions of galaxies, delivering precise rotation curves with a clarity and reach that today's instruments can only dream of. It will be able to detect the faintest tidal tails and stellar streams, the ghostly remnants of past mergers that have long since faded from optical view. Furthermore, by mapping the hydrogen in galaxies at different distances, and thus different points in cosmic time, the SKA will allow us to track how galactic rotations have evolved over billions of years, effectively creating a cosmic movie of spin evolution rather than a static snapshot. The synergy between these titans will be their greatest strength. The ELT might identify a peculiar galaxy with a suspected rotational anomaly, pinpointing the exact stellar populations involved. The SKA could then follow up, bathing that same galaxy in its sensitive radio gaze to map the distribution and motion of its gas, revealing how the invisible dark matter halo is shaped and whether it shows the lopsidedness that could cause gravitational torquing. Together, they will provide a complete, multi-wavelength autopsy of these cosmic puzzles. But the technological revolution doesn't stop there. Space-based observatories like the recently launched Euclid and the proposed LISA gravitational wave detector will contribute in profound ways. Euclid is meticulously mapping the shapes and positions of over 1 billion galaxies, and its incredibly sharp, wide-field vision will be instrumental in identifying statistical oddities like an unexpected prevalence of certain spin directions in galaxy clusters that could point to large-scale influences. LISA, designed to detect low-frequency gravitational waves, could sense the ripples in spacetime caused by the merging of supermassive black holes, the violent events that often sit at the heart of galactic mergers and whose energetic feedback might be crucial to flipping a galaxy's spin. This forward-looking excitement is about more than just bigger tools. It's about a fundamental shift in our approach to cosmic discovery. We are moving from an era of studying individual celestial specimens to one of immense statistical power. These new observatories won't just look at a few dozen anomalous galaxies. They will survey hundreds of thousands, even millions. This will allow astronomers to move from asking, "How can a galaxy spin the wrong way?" to the more powerful question, "Under what specific conditions do galaxies spin the wrong way?" By comparing vast numbers of normal and anomalous galaxies, we can identify the exact correlations BETWEEN Chinese letter rotation and other factors. A galaxy's mass, its environment, the age of its stars, the presence of an active nucleus, or the morphology of its dark matter halo. This big data approach will finally allow us to pinpoint the precise recipe, a pinch of merger, a dash of accretion, a sprinkle of dark matter clumpiness required to torque a galaxy into defiance. The optimism in the astronomical community is palpable because we are no longer just waiting for answers. We are actively building the machines that will unequivocally provide them, turning today's most perplexing cosmic mysteries into tomorrow's solved chapters in the grand story of our universe. Yet this cosmic puzzle does more than just humble us. It actively rekindles a primal sense of wonder that is often lost in our daily routines. There's a profound beauty in knowing that the universe is not yet fully known, that it still holds cards close to its chest. This mystery, and others like it, serves as a powerful antidote to intellectual arrogance, a reminder that the cosmos is under no obligation to conform to our expectations or timelines. It invites us to embrace curiosity not as a means to an end, but as a valuable state of being in itself. The very act of questioning why a galaxy spins the wrong way connects us to every human who has ever looked up at the night sky and felt a tug of awe, from ancient storytellers tracing constellations to modern physicists running complex simulations. It's a thread of inquiry that spans cultures and millennia, uniting us in a shared, timeless pursuit of understanding our place in the grand scheme of things. This enduring curiosity is what propels our species forward, driving innovation and artistic expression in equal measure. Furthermore, the collaborative effort to solve this mystery beautifully illustrates how science, at its best, operates as a profoundly human and collective endeavor. No single astronomer, no matter how brilliant, can unravel this alone. It requires the combined expertise of theorists who dream up new physics, observers who command vast telescopes, engineers who design unimaginably sensitive instruments, and data scientists who write algorithms to sift through mountains of information. This is a global undertaking with researchers from every continent sharing data, challenging each other's interpretations and building upon both successes and failures. The mystery of galactic rotation becomes a common focal point, a shared puzzle that transcends national borders and political divisions, reminding us that the quest for knowledge is a universal human trait that can bring people together in a common cause. It demonstrates that the scientific process is not a cold, mechanical accumulation of facts, but a dynamic, self-correcting, and deeply social conversation about the nature of reality itself. This journey also enriches our cultural and philosophical landscape, offering metaphors and narratives that resonate far beyond the confines of an academic paper. The image of a galaxy spinning against the current can become a powerful symbol of defiance, of unexpected beauty, or of the complexity inherent in any system. It challenges simplistic narratives and encourages a more nuanced view of the universe, one that acknowledges chaos and order as intertwined partners rather than opposing forces. Artists, writers, and philosophers can draw inspiration from this scientific frontier, using it to explore themes of mystery, perspective, and the limits of human perception. In this way, the scientific pursuit doesn't just provide answers, it feeds our collective imagination, contributing to a richer, more textured understanding of what it means to be a tiny, conscious part of a vast and still mysterious cosmos. Now, let's bring this cosmic mystery into sharp focus with a single, captivating celestial object that has become a legendary case study for astronomers, the galaxy known as NGC 4622. Located about 200 million light-years away in the constellation Centaurus, this spiral galaxy appears at first glance to be a perfect cosmic pinwheel. But a closer look reveals something deeply strange, a characteristic that has earned it a special place in the halls of astronomical puzzles. When researchers analyzed images from the Hubble Space Telescope, they noticed that its elegant spiral arms seemed to be winding in a direction that defies all conventional logic. Typically, in a spiral galaxy, the arms trail behind the direction of rotation. If a galaxy spins clockwise, the arms should trail in a counterclockwise direction, and vice versa. But NGC 4622 presents a stunning contradiction. The most prominent, well-defined arms appear to be leading arms, sweeping forward in the direction of rotation as if the galaxy is spinning backward. This is the equivalent of seeing a hurricane in which the spiraling clouds are whirling outward instead of inward, a sight that challenges our most fundamental understandings of fluid dynamics and motion on a galactic scale. The plot thickens considerably when we move beyond its appearance and delve into the actual kinematic data, the measurements of how its stars and gas are truly moving. This is where the puzzle transforms from curious to profoundly baffling. By using the Doppler effect to map the velocities across the galaxy, astronomers expected to find a clear motion that matched the leading arm structure. But the data refused to comply. Some studies of the galaxy's outer regions suggested a rotational motion that was entirely at odds with the story the spiral arms were telling. The evidence seemed to point in two different directions at once, creating a cosmic standoff between what we were seeing and what we were measuring. This conflict is what makes NGC 4622 such a perfect laboratory. It embodies the very heart of the scientific process, where observation and theory engage in a tense and fascinating dialogue, each forcing the other to refine and reconsider. In the face of such a contradiction, the astronomical community has naturally split into different camps, each championing a compelling explanation. One prominent theory argues that we are witnessing the aftermath of a dramatic galactic merger. The idea is that a smaller satellite galaxy was drawn into NGC 4622's gravitational grasp and was ultimately consumed. This violent event would have sent powerful shockwaves through the larger galaxy's disk, disrupting its orderly rotation and potentially flinging out new spiral arms in the process. If this incoming satellite had a significant amount of angular momentum in the opposite direction, it could have imparted that motion to the outer disk, creating a scenario where the inner and outer parts of the galaxy are rotating in opposition. The beautiful leading arms we see today in this scenario would not be the original arms, but rather new structures born from the chaos of that ancient collision, a permanent scar from a past cosmic trauma. However, a competing school of thought offers a radically different interpretation, one that serves as a crucial lesson in the humility of cosmic observation. This theory suggests that there may be no anomaly at all. Instead, it proposes that we are being fooled by a simple trick of perspective. Our view of NGC 4622 is not a clean, top-down shot. We see it inclined at an angle. This projection effect can make the geometry of spiral arms incredibly difficult to interpret correctly. Proponents of this view argue that what we are classifying as a leading arm might actually be a classic trailing arm that is being viewed from a specific and unfortunate angle, creating an optical illusion on a monumental scale. They point to sophisticated computer models that can reproduce the galaxy's apparent structure through certain combinations of tilt and arm morphology, without requiring any bizarre physics or historical collisions. This possibility forces us to confront a fundamental limitation. Even with our most powerful telescopes, we are still interpreting a three-dimensional universe from a two-dimensional image, a fact that can lead even the most careful scientists down a path of misinterpretation. The enduring mystery of NGC 4622 is not a mark of failure but a testament to the intricate detective work that defines modern astrophysics. It exemplifies how a single, peculiar object can become a crucial testing ground for our theories. Researchers run high-resolution simulations, inputting different merger scenarios to see if they can generate a galaxy that looks and moves just like this one. They develop new statistical methods to better determine the galaxy's true inclination and rule out projection effects. They comb through data from multiple wavelengths of light, looking for faint tidal streams or other debris that would be the smoking gun of a past merger. This galaxy has become more than just a subject of study. It is a benchmark, a cosmic riddle that challenges us to improve our methods, sharpen our questions, and acknowledge that sometimes the universe's greatest secrets are hidden not in the broad trends, but in the captivating details of a single, spinning island of stars. But the story of a galaxy's rotation doesn't end with the dramatic crashes of mergers or the subtle tugs of dark matter. There is a far more continuous and stealthy process at work, a slow and steady feeding that can, over billions of years, fundamentally reshape a galaxy's spin. Think of a galaxy not as an isolated island, but as a living entity within a vast cosmic ecosystem, one that must constantly feed on fresh fuel to sustain itself. This fuel is primordial hydrogen gas, the same basic material from which the first stars were born, and it permeates the vast spaces between galaxies in a diffuse web. Galaxies are constantly moving through this intergalactic medium, and as they do, they gravitationally attract this gas, pulling it in from their surroundings in a process known as accretion. This isn't a violent event, but a gentle, persistent rain of new material onto the galactic disk, and it carries with it a hidden power, the power of angular momentum. This incoming gas doesn't arrive empty-handed. It brings its own directional history, its own memory of motion from whatever cosmic structure it originated from. If a vast stream of this intergalactic gas begins to flow into a galaxy from a particular direction, it carries with it a specific angular momentum. Imagine a galaxy spinning peacefully like a giant carousel. Now imagine a group of people running alongside it and jumping on, but they're all running in the opposite direction to the carousel's spin. their sudden addition would jerk the entire platform, slowing its original rotation and perhaps even starting to push it the other way. This is the essential principle of gas accretion. If a significant amount of gas flows in from a direction that is opposed to the galaxy's existing spin, it doesn't just add mass, it adds a counteracting spin. Over hundreds of millions of years, this persistent influx can act as a steady hand on the galactic wheel, gradually applying a torque that breaks the original rotation and can, given enough time and the right conditions, actually reverse it. This isn't a quick flip but a slow, cosmic-scale realignment, a testament to how patient, persistent forces can achieve what sudden violence accomplishes in a merger. We are not merely theorizing about this gentle cosmic piracy. Our telescopes have caught it in the act. Observations of gas-rich galaxies, particularly in the early universe, frequently show the telltale signatures of these massive inflows. Using instruments that can detect the faint radio emission of cold hydrogen gas, astronomers have mapped vast rivers and streams of material flowing into galaxies, often from the cosmic filaments of the dark matter web. In some stunning cases, the motion of this infalling gas, measured by the Doppler shift of its light, clearly shows it moving in a direction that is misaligned or even directly opposed to the rotation of the galaxy's stellar disk. It's like watching a weather front of contrary motion slowly moving in, a storm of new momentum that promises to change the galactic climate for eons to come. These observations provide direct, tangible evidence that galaxies are open systems, forever drinking from the intergalactic well and forever being changed by what they consume. The virtual universes created by supercomputer simulations lend powerful support to this idea. In these intricate digital models, programmers can watch the entire life cycle of a galaxy unfold. They see how gas, governed by gravity and hydrodynamics, naturally flows along the dark matter filaments of the cosmic web, funneling into the waiting gravitational potentials of growing galaxies. The simulations consistently show that this accreted material can and does exert a significant torque on the galactic disk. The models can even quantify it. If the incoming gas stream has sufficient mass and its angular momentum vector is pointed in the right, or rather, the wrong direction, the simulation will show the galaxy's rotation rate slowing, stalling, and eventually beginning to spin the other way over billion-year timescales. This ability to not just predict but visually demonstrate the process in a controlled environment gives astronomers tremendous confidence that gas accretion is a legitimate and powerful mechanism for altering galactic spins, a third major player alongside mergers and dark matter in the grand mystery of cosmic rotation. While the immense gravitational pull of dark matter and the violent drama of mergers often take center stage, the seemingly empty spaces between galaxies hold their own subtle yet persistent influence. This isn't a perfect vacuum. It's filled with the intergalactic medium, or IGM, a gossamer thin soup of mostly hydrogen gas and plasma that permeates the entire cosmos. Though its density is vanishingly low, perhaps just 1 atom per cubic meter, its cumulative effect across the vast expanse of a galactic disk can be significant. Imagine a giant sailing ship moving through a calm ocean. Even the slightest breeze and the gentle pressure of the water against the hull will, over a long enough voyage, influence its course and speed. A galaxy sailing through the IGM experiences a similar, constant hydrodynamic pressure. This pressure isn't strong enough to stop a galaxy in its tracks, but it can exert a gentle, persistent force on its outer gas disk. Over hundreds of millions of years, this constant push can act as a subtle brake on the galaxy's rotation, or, if the pressure is uneven, apply a slight torque that ever so gradually alters its spin axis. It's a testament to how even the faintest forces, given cosmic timescales to operate, can contribute to the grand narrative of galactic evolution. But the influences don't only come from outside. Galaxies themselves can generate powerful winds that blast material back out into the IGM, and in doing so, they can fundamentally alter their own internal dynamics. The most dramatic of these outflows are cosmic winds, colossal gusts of gas that are driven by two powerful engines within the galaxy itself. The first is the collective fury of star formation. In regions where stars are being born at a ferocious rate, the most massive of these new stars live fast and die young, exploding as supernova within a few million years. Each of these explosions is a titanic event, and together they can heat the surrounding gas to immense temperatures and blow it clear out of the galaxy in a supernova-driven wind. The second engine is even more powerful, the active galactic nucleus, the supermassive black hole at the galaxy's core. When actively feeding, it can launch jets and outflows that inject staggering amounts of energy into the galactic system, driving winds that can reach speeds of thousands of kilometers per second. The crucial thing to understand about these winds is that they don't just carry away gas, they carry away angular momentum. Angular momentum is the conserved quantity that keeps a galaxy spinning, and it's a finite resource. Think of a spinning ice skater. When they pull their arms in, they spin faster because they concentrate their mass and angular momentum. But if they could somehow throw their arms away, they would lose that angular momentum and their spin would slow down. A cosmic wind does exactly that to a galaxy. As it blasts gas out into the void, it literally throws away a portion of the galaxy's angular momentum. This loss has a direct braking effect on the galaxy's rotation. It's a process known as angular momentum transport, and it can gradually slow the spin of the entire galactic disk. In extreme cases, if the wind is asymmetric, blowing out more forcefully from one side of the galaxy than the other, the resulting loss of momentum could be uneven, potentially applying a torque that contributes to a change in the spin direction over billions of years. This means the very processes that create stars and feed black holes can, through their own feedback, act to slow down or reshape the rotation of their host galaxy. The evidence for this intricate interplay between a galaxy and its environment is growing stronger, thanks to astronomers who compare galaxies in different cosmic settings. We see telling correlations that strongly suggest external gas pressures play a role in shaping rotational properties. For instance, galaxies that are falling into the dense core of a massive cluster for the first time experience a tremendous increase in pressure from the hot, dense IGM that fills that cluster. This phenomenon is known as ram pressure stripping. As a galaxy plunges through this intracluster medium, the external gas acts like a mighty wind, trying to strip away its own interstellar gas. This violent interaction can severely disrupt the galaxy's gas disk, removing its fuel for future star formation and directly affecting its dynamics. Studies have found that galaxies undergoing this process often show disturbed or anomalous rotation curves, their once orderly spin patterns scrambled by the intense external forces. Conversely, galaxies that reside in quiet, isolated voids regions of space with a very low density of both galaxies and IGM often display more predictable and orderly rotation, having evolved for eons without such dramatic external interference. This environmental dependency is a powerful clue. It demonstrates that a galaxy's rotation is not solely an internal affair, but is also a product of its address in the universe, shaped by the pressure and flow of the galactic ecosystem that surrounds it. Yet for all the chaos of crowded galactic cities and the subtle pressures of intergalactic winds, some of the most profound rotational mysteries are found in the cosmic countryside, the vast, empty voids where galaxies drift in near total isolation. These solitary giants, spinning contrary to expectation with no neighbors in sight, present a challenge that cuts straight to the heart of the matter. If a recent, violent merger or a close gravitational encounter can't be the culprit, as there's simply nothing nearby to cause such a disturbance, then our explanations must stretch back across eons or delve into the very birth of the galaxy itself. It forces a monumental shift in perspective, pushing us to consider that the answers may not lie in dramatic external events, but in the slow, internal simmer of a galaxy's own deep history or the unique conditions of its creation. Consider the life of such an isolated galaxy. It has spent billions of years in serene solitude, far from the gravitational tug of war that defines dense clusters. Its rotational signature, therefore, is a pristine record, unblemished by recent cosmic traffic accidents. This purity makes its anomalous spin not a complication, but a clue of unparalleled value. The cause must be either incredibly ancient or intrinsically internal. One compelling possibility is that the galaxy was simply born that way. The primordial cloud from which it collapsed may have possessed a peculiar and strong initial spin, a rotational quirk imprinted by the specific tidal forces of the dark matter filament it formed within during the early universe. In this scenario, the galaxy isn't spinning the wrong way at all. It's spinning exactly as it was always destined to, a unique product of its particular place and time in the cosmic web's infancy. Its isolation has simply preserved this original signature, like a sealed time capsule, allowing us to see a spin state that has been overwritten by interactions in virtually all other galaxies. Alternatively, the explanation might not lie at the very beginning, but in a long-forgotten chapter of its middle age. Even an isolated galaxy may not have always been alone. Billions of years ago, when the universe was younger and denser, it could have had a companion, a smaller satellite galaxy that shared its space. If this dwarf companion was gradually devoured in a slow, minor merger event, the larger galaxy would have absorbed its stars, its gas, and crucially, its angular momentum. If the satellite was orbiting in a retrograde direction, its assimilation would have imparted a counterspin to the host. Over the immense eons that followed, the gravitational evidence of this feast would have faded. The tidal streams of stripped stars would have dispersed, becoming far too faint for our current telescopes to detect, and the galaxy would have relaxed back into a smooth, serene disk. The only remaining evidence of this ancient act of cosmic cannibalism would be the galaxy's stubbornly reversed rotation, a silent ghost of a long-dead companion whose only legacy is a twist in the motion of its consumer. This pushes the frontier of galactic archaeology to its absolute limits. To solve this mystery, we must become cosmic genealogists, tracing a galaxy's family tree back across time. This requires more than just a snapshot of its current state. It demands a detailed reconstruction of its entire life story. Astronomers approach this by studying the galaxy's stellar populations with extreme precision. By measuring the ages, chemical compositions, and motions of hundreds of thousands of individual stars, they can look for subpopulations that tell different stories. The discovery of a group of stars that are all the same age, all moving in the opposite direction to the main disk, would be the smoking gun of that ancient merger. Their metal content could even date the event, telling us precisely when in cosmic history this transformative encounter occurred. For a galaxy that was born with a strange spin, we might instead find that all its stars, from the oldest to the youngest, share the same rotational signature, indicating the spin was set in stone from the very first moment of star formation. The existence of these isolated anomalies is perhaps the most humbling aspect of this entire mystery. They are a stark reminder that a galaxy's evolution is a story written over billions of years, and we are merely glimpsing a single page. Our telescopes, for all their power, often lack the sensitivity to see the faintest echoes of these ancient events. It challenges us to build better instruments and develop more sophisticated simulations that can model the entirety of a galaxy's lifespan, from its first collapse to its quiet old age in isolation. These solitary spinning puzzles teach us that to truly understand a galaxy, we must know its entire history, not just its present company. They force astronomy to think in deeper time, connecting the instantaneous physics of a collapsing gas cloud to the patient, billion-year consequences that unfold in the quietest corners of the universe. When the well-tested paths of dark matter and galactic collisions still leave us with unanswered questions, the most adventurous minds in theoretical physics begin to wander into far more speculative territory, exploring exotic concepts that sound like they belong in science fiction. This isn't about abandoning the known laws of physics, but about stretching them to their absolute limits, considering possibilities that are currently untestable but mathematically intriguing. These ideas are the cutting edge of cosmology, the wild hunches that, while highly speculative, serve a vital purpose. They break us out of conventional thinking and force us to consider the universe as a place that might be far stranger and more wonderful than we have yet dared to imagine. The mystery of Chinese letter spinning galaxies provides the perfect catalyst for this kind of creative exploration, a puzzle so persistent that it justifies asking, what if? One of the most fascinating of these exotic proposals involves cosmic strings. These aren't the strings of string theory, but hypothetical one-dimensional defects in the fabric of spacetime itself, thought to have formed during a phase transition in the universe's earliest, superheated moments, much like cracks freezing into ice. A cosmic string would be a filament of pure energy, thinner than a proton but possessing unimaginable density, with a single inch of it potentially weighing more than a mountain. Their gravitational influence would be utterly bizarre. Because they are under immense tension, they would warp space-time around them in a unique way, creating a gravitational field that doesn't pull inward like a planet, but instead exerts a double-edged repulsive force on objects passing by. If such a string were to exist and drift through a galaxy, its peculiar gravity could act like a cosmic scalpel, slicing through the galactic disk and applying an incredibly powerful and precise torque. The galaxy wouldn't be pulled toward the string, it would be sheared by it. This gravitational shearing effect could, in theory, impart a sudden and dramatic change in the galaxy's angular momentum, potentially flipping its spin axis or setting it rotating in a new direction without the need for a collision or a dark matter anomaly. It's an elegant, though entirely unproven, solution that attributes the mystery to a chance encounter with a relic from the absolute dawn of time. Another speculative idea points the finger at primordial black holes. These aren't the stellar mass black holes formed from collapsing stars or the supermassive ones at galactic centers. Primordial black holes are a hypothetical class that could have been forged directly from the extreme densities of the Big Bang itself, making them potentially as old as the universe. They could range in size from smaller than an atom to larger than a star, and some theories suggest they could constitute a portion of the dark matter we've been searching for. Now, imagine a galaxy's rotation being influenced not by a smooth halo of dark matter particles, but by a few massive, ancient black holes lurking in its outskirts. A primordial black hole with the mass of a star or even a planet would be too small to see directly, but its gravitational influence would be highly localized and potent. If one of these invisible behemoths were on a specific, high-speed trajectory through a galaxy's halo, a gravitational slingshot maneuver, it could transfer a significant amount of angular momentum in a very short cosmic time. Like a bowling ball rolling through a cloud of pins, its passage could create a temporary but powerful gravitational disturbance, a wake that could torque the gas and stars in the galactic disk, leaving behind a rotational anomaly that persists long after the black hole has continued on its journey into the void. This turns the mystery into a cosmic needle in a haystack hunt, where the culprit is a lone, ancient, and invisible wanderer. The value of these speculations isn't necessarily their immediate verifiability, but their power to inspire new modes of thought and to drive technological innovation. The mere possibility of cosmic strings, for instance, has motivated astronomers to scour the cosmic microwave background for their faint, telltale signatures, and to develop ever more sensitive methods for detecting gravitational waves, which might ripple from their vibrations. The hunt for primordial black holes pushes us to refine our techniques in gravitational microlensing, where we watch for the brief brightening of a star as an invisible object passes in front of it and bends its light. Even if these specific ideas never pan out, the process of investigating them almost always leads to unexpected discoveries. It was the search for the hypothetical planet Vulcan that helped refine our understanding of Mercury's orbit, ultimately leading to Einstein's theory of general relativity. In the same way, the relentless pursuit of an explanation, FOR Chinese letter spinning galaxies, keeps the entire field of cosmology dynamic and forward-looking, ensuring that we never become complacent in our understanding. These exotic theories are the lifeblood of fundamental science, representing a courageous willingness to ask big questions even when the answers lie beyond our current grasp, reminding us that the universe's greatest secrets often demand that we first expand the boundaries of our own imagination. And perhaps one of the most beautiful aspects of this cosmic mystery is that you don't need a PhD or access to a multi-million-dollar telescope to contribute to its solution. The quest to understand why galaxies spin the wrong way has been flung wide open to the world, thanks to the incredible rise of citizen science. Online platforms have transformed the living rooms and coffee shops of everyday people into vital extensions of the professional astronomy community, proving that the most powerful tool for discovery isn't always a bigger lens but a broader perspective. This is about more than just crowdsourcing data. It's about building a global community of curious minds, all working together to decipher the universe's most stubborn secrets. At the forefront of this movement is a project called Galaxy Zoo, which began with a simple yet revolutionary idea. Astronomers found themselves overwhelmed with digital images from robotic sky surveys, containing millions of galaxies that needed to be classified by their shapes. This was a task that the human brain, with its remarkable pattern recognition abilities, could do far more effectively than even the most sophisticated computer algorithm at the time. So they invited the public to help. The response was nothing short of astounding. Hundreds of thousands of volunteers from all walks of life, teachers, artists, retirees, students logged on to look at gorgeous images of galaxies and answer simple questions about what they saw. Is the galaxy smooth or featured? Does it have spiral arms? And if so, which way are they winding? This last question about the direction of the spiral arms is a key clue to the galaxy's rotation, and it's exactly where the keen eyes of volunteers have made their mark. The collective power of this human network has led to stunning serendipitous discoveries that automated scripts might have easily overlooked. Volunteers, who often develop a keen intuitive sense for the unusual, began flagging galaxies that looked odd. They found breathtaking objects that defied existing categories, which astronomers lovingly nicknamed green peas or red spirals. Most importantly for our mystery, they identified galaxies with peculiar, disturbed, or contradictory structures that suggested anomalous rotation. A volunteer might notice a galaxy where the inner arms seem to spin one way and the outer arms another, or a system with a bizarre polar ring of stars orbiting at a perpendicular angle to the main disk. These weren't just curiosities, they were the very clues that professional astronomers needed to pinpoint the most interesting candidates for further study with their large telescopes. The collective effort of the crowd acted as a massive filter, sifting through the cosmic haystack to find the most tantalizing needles. This engagement does far more than just accelerate research. It fundamentally reshapes our relationship with science. By participating directly in the process of discovery, people develop a deep personal connection to the cosmos. They aren't just passive consumers of pre-packaged facts. They are active contributors to humanity's understanding of the universe. A person who has classified 1,000 galaxies starts to see the night sky differently. They understand the immense diversity of galactic forms and appreciate that each shimmering smudge of light has its own unique story of formation, collision, and evolution. This experience fosters a genuine and lasting appreciation for the painstaking, often collaborative nature of scientific progress, breaking down the illusion that science is done by lone geniuses in isolated labs. It becomes a shared human endeavor. This collaborative model also serves as a powerful engine for inspiration, igniting passions that can shape futures. There are documented cases of amateur participants in these projects who became so captivated by what they found that they pursued advanced degrees in astronomy, turning a hobby into a career. For countless students and young people, the ability to make a tangible contribution to a real scientific problem is incredibly empowering. It demonstrates that the universe is not a closed book reserved for an elite few, but an open frontier waiting for anyone with curiosity and an internet connection. This spirit of open inquiry helps cultivate the next generation of scientists, engineers, and informed citizens, ensuring a future where the wonder of cosmic exploration continues to burn brightly. Ultimately, the story of citizen science and galactic rotation is a powerful testament to a new paradigm of discovery. It proves that the most intractable problems in science are no longer the sole domain of specialists. The mystery of why some galaxies spin the wrong way is being tackled by a global team, a seamless blend of professional astrophysicists who build the theories and telescopes, and the dedicated army of volunteers who bring their perception, their time, and their shared curiosity to the effort. It underscores a profound truth that the desire to understand our place in the cosmos is a universal human trait, and by harnessing that collective wonder, we can all play a part in peeling back the layers of the universe, one galaxy at a time. As we invest billions into building ever larger telescopes and supercomputers to simulate cosmic evolution, we must pause to ask a deeper question that extends beyond the physics of spinning galaxies. How do we, as a society, decide which cosmic mysteries are worth solving? The pursuit of knowledge, especially on these grand scales, is never free from ethical considerations. It forces us to confront difficult choices about the allocation of finite resources, both financial and intellectual. Consider the staggering cost of a project like the James Webb Space Telescope, or the upcoming extremely large telescope investments that run into the tens of billions of dollars. In a world facing pressing challenges like climate change, poverty, and disease, is it justifiable to devote such vast sums to understanding why a distant galaxy spins backward? This is not a trivial question, and it deserves a thoughtful, nuanced discussion that acknowledges the validity of both sides. Proponents of funding these ambitious projects argue that curiosity-driven research is the bedrock of long-term human progress. They point out that the technological spin-offs from space exploration and astronomy are immense and often unpredictable. The development of charge-coupled devices for capturing starlight revolutionized digital imaging, now found in every smartphone camera. The need to process vast astronomical datasets has driven innovations in computing and data science that ripple through countless industries. Furthermore, understanding our universe fulfills a fundamental human need to comprehend our place in the cosmos, a pursuit that has inspired art, philosophy, and science for millennia. To prioritize only research with immediate, tangible applications would be to stifle the very engine of discovery that has propelled our species forward. The mystery of galactic rotation may seem esoteric, but its solution could force a radical rewrite of physics, potentially revealing new aspects of dark matter or gravity that could have profound implications we cannot yet foresee. However, the counter-argument carries significant moral weight. The resources poured into a single telescope could alternatively fund global vaccination programs, build renewable energy infrastructure, or provide clean water to millions. This creates an ethical tension between investing in the future of human knowledge and addressing the urgent needs of humanity in the present. There is no easy answer, and the resolution likely lies in striving for a balanced portfolio. This means continuing to fund pure, basic science while also ensuring robust investment in applied research aimed at solving earthly problems. It also means that the astronomical community has a responsibility to communicate the value of its work effectively to the public, who ultimately fund these endeavors through taxes and philanthropy, demonstrating that understanding the cosmos is not a frivolous diversion but a vital part of our collective human endeavor. This leads to another critical ethical imperative, the democratization of discovery. The history of science is, unfortunately, also a history of exclusion. For centuries, vast swaths of the human population were barred from participating in the great intellectual pursuits. Today, we have an opportunity and an obligation to ensure that the quest to understand mysteries like galactic rotation is a truly global and inclusive effort. This means actively working to make astronomical data and research tools accessible to scientists and students in developing nations, not just those at wealthy institutions in a handful of countries. Open access policies, which make scientific papers freely available to anyone with an internet connection, are a crucial step in this direction. So too are initiatives that provide remote observing time on major telescopes or access to supercomputing resources for teams around the world. When we embrace this collaborative, open model, we don't just act ethically, we also accelerate science itself. The mystery of Chinese letter spinning galaxies is too complex for any single nation or research group to solve alone. It requires diverse perspectives, unique skill sets, and cultural viewpoints that can only come from a globally engaged community. By breaking down barriers to participation, we tap into a wider pool of human genius, increasing the likelihood of a breakthrough. This inclusive approach ensures that the profound insights gained from studying the cosmos, insights about the fundamental laws that govern all of existence, benefit all of humanity, and are shaped by contributors from all corners of our planet. The goal is not just to understand why a galaxy spins the wrong way, but to ensure that in the process we build a more equitable, collaborative, and enlightened global society here on Earth. Perhaps one of the most powerful places to witness this spark of curiosity is in the immersive environment of a planetarium. Under a domed ceiling that transforms into a window to the cosmos, students aren't just told about these rotational mysteries, they are transported directly into them. A skilled presenter can fly the audience through a three-dimensional simulation of a galaxy like NGC 4622, allowing everyone to circle the celestial object and see for themselves the perplexing contradiction between its spiral arms and its measured motion. This isn't a passive lecture, it's a cosmic adventure. The gasps from the crowd when the galaxy slowly rotates, defying all expectations, are a testament to the power of seeing science as a living, breathing detective story rather than a set of facts in a textbook. Planetariums make the vast scale and profound weirdness of the universe accessible, transforming abstract astrophysical concepts into a direct sensory experience that can ignite a sense of wonder in a way a diagram on a page simply cannot match. Back in the classroom, educators are using brilliantly simple hands-on models to make these grand concepts tangible. Imagine students standing in a circle, holding a large elastic sheet that represents the fabric of space-time. Placing a heavy ball in the center to simulate a galactic core, they then try to roll smaller marbles around it, mimicking the orbits of stars. Now introduce a second, smaller ball, rolling it in from an angle to represent an incoming satellite galaxy. The students can see and feel how the gravitational interaction warps their elastic sheet, sending the orbiting marbles into new, chaotic paths. This kinetic, collaborative experiment transforms the abstract idea of a galactic merger from a distant event into a physical reality they have created themselves. They aren't just learning about angular momentum, they are feeling it. This process of building, testing, and visualizing makes the science stick, moving it from a memorized fact to a deeply understood principle. The ultimate goal of this educational outreach extends far beyond creating the next generation of professional astronomers. It is about nurturing a fundamental scientific literacy and a mindset of critical thinking that benefits every member of society. When a student grapples with why a galaxy might spin the wrong way, they are practicing the very same skills needed to evaluate a news headline, assess a medical claim, or understand a complex policy issue. They learn that uncertainty is not a weakness but an invitation to investigate further. They see that experts can disagree and that the scientific process is a self-correcting, collaborative effort to get closer to the truth. This creates a public that is more engaged, more skeptical in the healthy sense, and more appreciative of the long, often challenging work of discovery. It fosters a culture that values evidence-based reasoning, which is essential for navigating the complexities of the modern world. By sharing the excitement of these unsolved cosmic puzzles, we are offering a powerful antidote to the notion that science is a closed book of settled answers. We are instead presenting it as the greatest ongoing story ever told, a narrative where each answered question reveals three new ones. A student who leaves a planetarium show captivated by the mystery of Chinese letter rotation carries that curiosity with them. It might lead them to build a better telescope in their backyard, to write a compelling science fiction story, to develop a new algorithm for analyzing data, or simply to look at the night sky with a newfound sense of reverence and possibility. This lifelong passion for inquiry is the most valuable outcome, ensuring that the wonder that drives scientific progress never fades, inspiring not just future scientists, but future artists, engineers, writers, and informed citizens who will all be enriched by a deeper connection to the universe they call home. This grand cosmic puzzle, the question of why some galaxies defy our rotational expectations, cannot be confined to a single department at a university. To truly chase an answer, we must welcome a chorus of voices from across the entire spectrum of human knowledge. This is not a challenge for astrophysics alone. It is a symphony of disciplines, each playing a vital part in the investigation. The mystery acts like a central hub with roads leading out to physics, mathematics, computer science, and even philosophy. And it is only by traveling down all of them that we can hope to reach a complete understanding. At its core, this is a problem of physics, demanding a deep grasp of gravity, angular momentum, and hydrodynamics. But the mathematics required to describe these forces, especially across such immense scales and over billions of years, is breathtakingly complex. Theorists develop intricate equations to model how dark matter halos evolve and how tidal forces transfer energy, creating the abstract frameworks that define the possible. Then, computer scientists take these mathematical blueprints and perform a kind of modern-day magic, translating them into immense cosmological simulations. They write the complex code that can bring a virtual universe to life inside a supercomputer, allowing us to run experiments that would be impossible in reality, testing thousands of different collision scenarios or dark matter models to see which ones produce the anomalous spins we observe. Yet the raw data from these simulations and from telescopes is a vast, often noisy ocean of information. This is where another set of experts comes in. Data scientists and statisticians develop sophisticated machine learning algorithms that can sift through this ocean to find the subtle patterns and correlations that a human eye might miss. They create tools that can classify the spin directions of millions of galaxies automatically, or identify the faint, ghostly tidal streams that are the telltale signatures of a long-ago merger. Their work transforms overwhelming information into actionable insight, turning data into discovery. And then there are the philosophers, whose role might seem the most abstract but is perhaps the most grounding of all. They step back from the equations and the data plots to ask the deeper questions that underpin the entire endeavor. What does it mean for a natural law if it appears to have exceptions? How do we reconcile the stunning order we see in most of the cosmos with the seemingly chaotic outliers? If a galaxy's spin is determined by a quantum fluctuation in the first instant of the universe, what does that say about causality and destiny on a cosmic scale? Philosophers of science help us examine the very assumptions and methodologies we use, ensuring that our quest for answers is built on a sound logical foundation and that we remain aware of the limits of our own knowledge. This collaborative spirit shatters the old stereotype of the lone genius working in isolation. Modern astronomy is a team sport, a global effort that connects a theorist working on dark matter particle physics with an engineer optimizing a telescope's camera, and a software developer writing an algorithm with a philosopher pondering the nature of scientific truth. They may speak different technical languages, but they are united by a shared, burning curiosity about the universe. This interdisciplinary dialogue is incredibly enriching. It forces each specialist to explain their work in clear, accessible terms, which often leads to new insights and prevents any one field from becoming too insular or set in its ways. The mystery of Chinese letter spinning galaxy, therefore, becomes more than just an astronomical oddity. It stands as a powerful testament to the holistic nature of scientific exploration, demonstrating that the biggest questions demand that we bring our entire intellectual toolkit to bear, uniting diverse fields in a common and profoundly human quest for understanding. Behind every perplexing data point and every anomalous rotation curve, there are astronomers who have devoted their careers to staring into the depths of space, driven by a mix of profound wonder and sheer stubbornness. Talking to these researchers, you quickly realize that this isn't just a technical puzzle for them. It's a deeply personal journey. There's a shared sentiment, a kind of affectionate frustration that comes from loving something so complex that it refuses to give up its secrets easily. They speak about the universe with a sense of awe that is almost reverent, describing the first time they saw a galaxy's spectrum reveal its contradictory spin not as a mere data acquisition, but as a moment of genuine conversation with the cosmos. It's the thrill of the chase, of knowing you're close to understanding something fundamental, paired with the humbling acknowledgement that the universe is always more clever than you are. The reality of this work is far from the glamorous image of an astronomer simply pressing a button on a telescope. It involves countless late nights at remote observatories, huddled against the cold, watching as the dome above you opens to the stars. There's the meticulous, often tedious process of guiding the telescope, of waiting for the exact moment of perfect atmospheric clarity, and the nerve-wracking fear that a technical glitch or a passing cloud will ruin hours of precious observing time. One researcher shared a story of waiting an entire year for a second chance to observe a particular galaxy, only to have the instrument fail minutes into the session. This is followed by the painstaking reduction of the data, the long hours spent writing and debugging complex code to model the results, and the slow, incremental progress that measures success in millimeters over years. The path to a potential discovery is a marathon run in the dark, lit only by the faint hope that the next observation might be the one that finally makes sense of it all. Yet, it's within this grueling process that the most human moments emerge, the sudden eureka, moments that make all the struggle worthwhile. An astronomer described the experience of staring at a plot on her screen for the 100th time, when suddenly a new way of interpreting the data clicked into place. It wasn't a loud celebration, but a quiet, overwhelming sense of connection, a feeling that she had uncovered a tiny piece of a truth that had been hidden for billions of years. These breakthroughs are rarely solo achievements. They're celebrated over rushed coffees with colleagues, in excited late-night emails, and during conference calls where voices crackle with excitement from across the globe. This collective endeavor, this shared burden and joy, is what transforms the frustrating pursuit into a deeply meaningful collaboration. Their perseverance in the face of such an immense mystery is perhaps their greatest lesson to us all. These are individuals who have chosen to spend their lives contemplating questions that may not be answered in their lifetime, and they do so with a radiant passion that is utterly contagious. They are inspired not by the guarantee of success, but by the value of the search itself. This long-term commitment is a powerful reminder that some of the most worthwhile journeys don't have a clear destination. It teaches a resilience that is applicable far beyond astronomy, the ability to remain curious and engaged even when answers are distant, to find joy in the process of learning itself, and to understand that every dead end is still a step forward because it tells you where not to look next. Their work is a testament to the human spirit's unyielding desire to understand its place in the universe, proving that the drive to explore is one of our most defining and noble traits. As we've journeyed through the enigma of galaxies spinning the wrong way, we've seen how this mystery intertwines dark matter, galactic interactions, and technological limits, challenging our understanding of the cosmos. This isn't just a story about astronomy. It's a profound lesson in humility, showing us that the universe is under no obligation to conform to our models or expectations. Every time we think we have it all figured out, a galaxy spinning in defiance shows up to remind us that there is so much more to learn. The clues we've gathered, from the gravitational whispers of dark matter halos to the violent ballet of galactic mergers, point toward a universe that is far more dynamic, interactive, and surprising than we ever imagined just a century ago. Our most powerful telescopes have brought us incredibly far, peering back to the dawn of time and mapping the cosmic web in stunning detail, yet they still haven't fully explained these rotational puzzles. This isn't a failure of science, but its greatest triumph, the recognition of our own limits, is what propels us forward. The fact that there are questions we cannot yet answer is what keeps the field alive, vibrant, and endlessly fascinating. It leaves ample room for wonder, for the kind of awe that first draws us to look up at the night sky, and for the patient, persistent curiosity that drives the next generation of explorers to build even better tools and ask even bigger questions. So remember, each of those unexplained spins out there is not a frustrating dead end, but an open invitation. An invitation to explore deeper into the physics that governs all existence, to think bigger about our place in the cosmos, and to stay endlessly curious about the universe's boundless capacity for surprise. This mystery, like all great cosmic puzzles, belongs to everyone. It invites us all to be participants in the great human adventure of discovery, whether we're professional astronomers analyzing data or simply people who occasionally glance up at the stars and feel a sense of wonder. If this journey through spinning galaxies has sparked your imagination, we would love to hear what you think. What theory for THESE Chinese letter rotations resonates most with you? Share your thoughts and questions in the comments below. Let's keep this conversation about the universe going. For more deep dives into the cosmos's greatest mysteries, make sure to subscribe and hit the notification bell so you don't miss our next cosmic adventure. Never stop asking questions, and most importantly, keep looking up. The universe is vast, mysterious, and filled with wonders waiting for you to discover them. The next great mystery is out there, just waiting to capture our collective imagination.